I mentioned in the last video that when we do double slit experiments, we almost always use a single wavelength of light, okay? But what if we didn't? What if we sent white light through it? Well, we could simply look at this relationship. So d sine theta equals m lambda, and we could kind of predict what would happen if we did a double slit experiment, but we were ultimately sending through many, many different wavelengths, okay? All kinds of different colors, right? All the different lambdas, in other words, okay? What would happen? Well, here's the thing. If sine theta, right, in other words, really we could just say theta equals inverse sine of m lambda over d, right? Right, because sine theta will be m lambda over d. So we can tell from this that theta is linked with lambda, okay? So if we're sending in many, many different wavelengths, then we're going to get many, many different angles. We're going to get a different angle for every wavelength. So just like we can see in this picture, we would actually see almost like a prism, this kind of spreading of this dispersion of the colors of the visible light spectrum, okay? And since red has the longest wavelength, the red lambda is longest, right? Then we know that we would expect to see red to be the farthest out. Okay, so there's a few questions that go along with the slide. One is, why does Young's experiment separate white light into its constituent colors? Well, simply because this relationship says that for every lambda, there's going to be a different angle. So you're going to get that separation. Okay. 2, in the group of colored fringes, such as the 2 singled out, why is red farther out? Once again, if red has the greatest lambda, you're going to get the greatest theta. Okay, so it'll have bent farther, okay? And why is the central fringe white rather than colored? Okay, well, here's the thing. If we're talking about the central fringe, we're talking about m equals 0, right? And when sine theta equals 0, that only happens in one case, and that's when theta equals 0, right? And so that means that there's no deflection, right? If theta equals 0, there's no deflection. And all of those wavelengths, for m equals 0, every single wavelength will still have a 0 angle. And so it'll totally line up directly in front of the 2 slits as a beam, a bright, big white fringe. Okay? Hope that makes sense. All right, we're going to go on to the first misconception question of the week. So light passing through a double slit arrangement, like this, is viewed on a distant screen, like this. So this goes here, and this lands here. We have this nice overlap. The interference pattern observed on the screen would have the widest spaced fringes for the case of, well, we already know that. The fringing, in other words, the theta, is the biggest when the wavelength is longest. Red has the longest wavelength, so that would have to be red light. That automatically chops out B and D, right? Now here's the thing. Theta also increases if D gets smaller, right? So which of those remaining, A or C, has a small d, or a small slit spacing? Because remember, the slit spacing here is D. Well, sure looks like it would be A to me. So A, red light and small slit spacing, is going to give you the widest space fringing because theta is going to be the greatest in that case. All right. So why do I share all this? I share all this because just using this one relationship that we derived, this very, very simple relationship, we can know a lot. We can predict a ton about what we expect to happen in a double slit experiment with different wavelengths of light, at different fringes, with different spacings. There's a lot that we can predict, and more in science, I want to flesh out using simple relationships. How do we squeeze all the blood that we can from a simple equation, from a simple relationship, to learn and investigate as much as we can about some scientific phenomenon? Okay, The last thing I want to share in this video is this concept of thin film interference. And this is something I'm sure you've all seen before, right? Have you ever seen, like, there'll be like a puddle and maybe some gas got in it or some oil got in it, and it has almost these these interesting fringes that are multicolored and almost like a rainbow. You can see it in this picture in this slide here. So this is called thin film interference. And the reason why this happens is because incident light on a surface will bounce off two surfaces because you have two substances. Okay, so let's say that we have incident light on some surface, okay, and it refracts a little bit. And let's say this is air, this is the atmosphere, right? This is gas, some gas leaked into this little puddle, and this is the water, right? Okay, so you know that part of the light is transmitted and part of the light is reflected. And when the light goes through the gas, part of it will get, transmitted into the water, and part of it will get reflected. But these two beams, these are different. This is the air gas beam, and this is the water gas beam, right? And those will interfere with each other, and you're going to get your own constructive and destructive interference. And different wavelengths are going to interfere in different ways, and so you're going to end up getting this beautiful rainbow effect. So again, this kind of explains a natural phenomenon that you saw, that you probably thought was cool, but didn't really understand the physical mechanism. It's simply because at different surfaces you have light reflecting off those different surfaces, bouncing off, interfering with each other, causing fringes, different wavelengths interfering with each other for different maximum bright fringes and dark fringes, and you end up getting the kind of chaotic cyclone of color that you see in these puddles. All right, in the next video, we're going to talk about the next big concept, which is diffraction.